So in this 16 slides, I want to explain parsing and context-free grammar very quickly. So this is constituency-based parse tree, also called syntactic parse tree. So you go from these terminals, ball, the, hit, John, to the pre-terminals such as ND, and then to the non-terminals such as MP, VP, S. And this is good because you understand the grammar. Also, the grammar says something naively about semantic things, but not always. So that's why this syntactic parse tree could be used for many things, such as dependency parsing and also semantic parsing a little bit. And there are articles that to solve their semantic parsing problems using syntactic parsing in Stanford. And we can parse tree of an image as well. So image is like a sentence for me. Film is like a text for me. So you see how all of these analogies could be used for different problems. And also DNA. And so the more I learn about our body and DNA, I understand that DNA is the true language of our body. So our body talks. When we have a disease, our body is talking to each other. All of these proteins, all of these CTA, the combination of them, especially in the three-dimensional world that they live, they are talking to each other, how they are aligned with each other, what happens, what processes happens. It's very fascinating that it's like, so parsing a DNA is really interesting in order to have an interpretable approach to these bioinformatics. So this playlist focuses on context-free grammar. And you can go from context-free grammar to context-sensitive. But this context-free is enough for us. We don't need to add. There are lots of generalization of context-free grammar. For example, sometimes it is not enough. That's why we go from context-free grammar to lexicalized context-free grammar, or even more. Even you go to even other paradigms such as CCG, combinatory categorical grammar, which I explained in another playlist. So the Chomsky, the biggest guy in linguistics in the world, is very nice. If you have seen his lectures on YouTube, very old lectures, you will see how beautiful he looks at the language, that even computer scientists cannot think about that abstract. So you will see that even linguists can be more creative than computer scientists, and he's really genius in the way he created these basic building blocks so that computer scientists can now use it for machines. Otherwise, we didn't know how to deal with these complex ambiguities in our natural language. And also the relationship between different languages, so cross-linguistics, and how, for example, I believe that CCG, combinatory categorical grammar, could be used for cross languages. So it's language independent. It could be used for all languages. So it could be the next biggest standard approach. Universal approach to anything. Universal approach to semantic parsing, anything. So the CFG formalism, as I said, you have some terminals, then you have some pre-terminals, and then you have these green non-terminals. And always you start from S symbol, which is a start symbol. So that's the beginning of everything. The non-terminals, as you see, the pre-terminals are this, part, and the terminals are just the words in your vocabulary. So example of a parse tree and a CFG grammar rule. For example, this start could be NPVP, but this NP could go either to adjective noun or determiner noun. So this makes ambiguities. We don't know which one to use. That's why we learn it. Just like the part of speech, you want to see what are the part of speech of a sentence. So because at each word can have lots of part of speech tags. So here the same problem arises. Because you have different rules for a given head, MP, then this arises some ambiguities. So you should infer it. For example, anything that you can use. For example, the mixing approach of Christopher Manning, you can use that in a supervised fashion. You can use hidden Markov model as that guy in Google Brain used it. He used Bayesian kinds of HMM, and very interesting, he introduced super tags in the context of combinatorial categorical grammar. But what I want to point out is that whenever something becomes more than one, like this, it creates ambiguities. It generates ambiguity. You create, for each sentence, you have maybe exponential number of trees. So which tree is more probable? We will explain those things in future. So data for parsing experiment, we use Penn Tree Bank. It's very expensive. It has 1 million words and so it's very expensive to create. I don't know if for other languages it has been done for all other languages such as Persian. I don't think we have such a good tree bank for Persian or Greek or Hebrew language. So it's a pity that so we don't know how to create these tree banks for all languages because we don't have money to pay to these crowdsourcers. And so labeling is expensive and the world is in inflation. And so we don't know how to create these tree banks. So syntactic parsing defines grammatical relations. It is interesting because you are doing this parsing, syntactic parsing. It is also talking to you about the grammar, so you can understand the dependency architecture and from just these syntactic tree, you can also understand and infer about the dependency tree as well. So that's why dependency tree is really so that's why syntactic parsing is really useful for dependency parsing. And syntactic parsing is great for machine translation. If you use the concept of alignment in these beautiful papers, you will see that the next generation of machine translation is not just looking for some encoder, decoder, LSTM, and using attention. You can also leverage the idea of parsing, syntactic parsing, in order to outperform state-of-the-art models in machine translation or any other tasks, not just machine translation. So it's great for machine translation. There are lots of beautiful articles that use these as a leverage for improving the results of machine translation. And as I said, these rules, for example, MP goes to determiner and nominal. These rules, because you have different rules for one head, this creates ambiguity. So this ambiguity, it creates, for example, here we have two ambiguities. But as a number of your words grow, as they grow, the number of trees grows exponentially. And that's a big problem. So check which one is modifying which one, the technique of ambiguity. For example, if you want to understand why is this tree is like this, because in my pajamas is modifying this shot an elephant. So each one is modifying the other one. So the right child could be modifying the left child. Sometimes the left child is modifying the right child. And these techniques, we can use the techniques of modifying. You just use the word modifying, you understand if you're doing it correctly or not. But don't worry, these are the works of crowdsourcers, and we pay them to do this. And it has already been done for Penn State Tree Bank, so no problem. So let's look at this. Cops did use knife. This tree means cops did use knife, but this tree means cops did not use knife. So it's very interesting. And I wonder, when a child, my niece didn't use the tree bank to learn in her brain. She just used it by unsupervised learning. She learned it by herself. So we don't need these tree banks for all languages because it's expensive. We can use unsupervised learning. And finding these ambiguities, these parse trees are automatically generated in our brains. So we don't need to worry about the algorithms that machines learn. So we have some parse tree in our brain. That's why we exist. So there is no difference between a machine and a human anymore, because anybody, even a dog, if it can parse, then it understands as high quality as a person. And so the missing problem of a dog is that it doesn't have a language. So the thing that differentiates a human from an animal is just the language. We have more advanced languages. There are languages like birds and dogs. They are primitive languages. So they cannot think about abstract things because their language is limited. Once we teach a dog and a bird some more advanced vocabulary, then they can grow, they can start growing. So I think this is the end of this lecture.